like this. All right, welcome everybody to the session on quantum computing, what we call quantum informatics. My name is Chris Honen. I'm professor of quantum programming at the University of Edinburgh. I'm joined by some colleagues that will speak a bit later. But first, the first 10 minutes, I have the enviable task of telling you what quantum informatics is and what it's all about. So I'm going to try and do that in the next 10 minutes. So first, what is quantum informatics? It's about what are carriers of information. Traditionally, in traditional computers, these are transistors. They carry bits, right? They're zeros or ones. And these bits have been getting smaller and smaller over time, the transistors that carry the bits. So the picture on the left is a 3 nanometer chip, which means the transistors in there are 3 nanometers small each. And on the graph on the right, you can tell that this is really, really, really small. Right? This is smaller than a human hair, and it's way smaller than anything you can think about in your daily life intuition. So that means that these kinds of scales, when the transistors get smaller and smaller, they obey not the laws of classical mechanics, but the laws of quantum mechanics, and some weird stuff can happen. This has been happening since, I think, I'm not exactly sure of the state of the art, but current things you can buy in the shop are like 5 nanometers. And from 7 nanometers down, there's already quantum effects playing a role now. And as they're going to get smaller and smaller, there's going to be more and more quantum effects. So I'm going to tell you a tiny bit about how this quantum information works. So I was saying a typical classical bit is either 0 or 1 and nothing else, right? It's one of the two and nothing in between. So that's like the picture on the left. A quantum bit, on the other hand, so a piece of information that's carried by a quantum mechanical system, can be anywhere on the surface of a three-dimensional sphere. So think about a football. Any point on the surface of the football is a possible value for a quantum bit, and these are the pictures on the right. So you can think about the North Pole and the South Pole of the football as being 0 and 1, the classical bit, but there's all this other stuff in between too, and that's called superposition. And this is one of the two tricks that make quantum computing really useful. The other trick is called entanglement, and this is a really weird phenomenon that we really do not have an analog for in everyday intuition if you walk around the street. And this is the fact that if you have 2 of these quantum bits, so the previous slide was about 1 single quantum bit, if you have 2 of them, they can be in such a state that if you look at one of them and ask it, what is your value? You know exactly what will happen if you ask the other one its value. So they're sort of linked in some way. But we can share 2 of these entangled quantum bits. I can keep 1 here. You can go to China on a holiday. It will still hold. So that's a very weird phenomenon that's called entanglement. And that's, I'm going to say, the second basis for a lot of the tricks that we use to make quantum computation useful. So to answer the question, what is quantum informatics? Our official tagline is, it's the study of transformation of quantum information, especially to and from its classical form. So as I was saying, a measurement, if you ask a quantum bit, what is your value? You sort of convert its quantum information to classical information because it will say 0 or 1. So that's a very short bit about the physics of it, about what does quantum informatics mean. Now let's go on to what is quantum informatics good for? So I focused a bit on the physics so far, and this is a whole wide field of what's more broadly called quantum technology. How can you use these sort of tiny systems to make machines or other apparatuses that do useful things for you? So for example, you can build GPS systems that are based on quantum properties. You can build atomic clocks that are fantastically precise. You can build magnometers that measure magnetic fields and electric fields and that kind of thing very precisely. That's called quantum sensing. This is not what we're going to be talking about today. That's very cool, don't get me wrong, but it's not what we call quantum informatics. So what is quantum informatics good for? We use these pieces of quantum information to make computations and to answer questions that you can encode in a quantum computation. So typical computations that quantum computers are good at are optimization. So this is a very broad thing where generally you have some sort of landscape with ups and downs, and you're trying to search for the lowest point in the landscape, say, or the highest peak in the landscape. Now, there could be optimization of some financial portfolio. It could be optimization of flight paths. It could be optimization of logistics in a warehouse. This is a very broad thing where you're sort of searching for the best solution to a certain problem. And that's something that quantum computers are typically very good at. And we'll hear a bit more about that from Oliver, Mario, and Ross later on. Second kind of thing that quantum computers are very good at is what's called quantum simulation. So this is where you're trying to model a problem from, let's say, quantum chemistry or drug discovery, where the problem is really about these sort of tiny physical systems and the quantum interactions between them are really important. Of course, it makes sense to simulate such a thing on a computer that sort of natively works and understands these interactions, because if you try to encode these interactions on a classical computer, you have to make all kinds of what's the opposite of shortcuts? Expansions, I guess, to make things work. So this is very useful in, as I was saying, material science and chemistry and drug discovery. That's another area quantum informatics is pretty good at. What else is quantum informatics good at? The third thing I'm going to mention has to do with cybersecurity. And this is what you may have heard in the news a lot about. And there's two sides to this story. So one side is, what if the bad guys have a quantum computer? Should I be afraid? Because one famous algorithm that is very quickly to do on a quantum computer, and we think is very hard to do on a classical computer, is called factoring. I give you a big number and ask you, find me a prime number that divides this. That's something quantum computers can do relatively efficiently. And it's also something that the RSA crypto system is based on. And this is the basis for a lot of secure communication between you and your bank, for example. So if the bad guys have a quantum computer, they could crack that and listen into all your communications, and that's not good. The flip side of the story is that we can use these weird interactions between quantum bits in a positive way. They also give us new opportunities that we didn't have before when we just had classical bits. So quantum informatics is very good at communication protocols. For example, there's something called quantum key distribution that we can use to communicate with each other securely, but that's now secured sort of by the laws of nature, and nobody can interfere with that other than, you know, tinkering with the machines. And in fact, this has been demonstrated on such scale that the Chinese government has satellites lying in the air and fiber optic links over the ground all the way from Shanghai to Beijing, so that they can securely communicate between the two endpoints. And this quantum communication gives other possibilities that weren't there before that have to do with, for example, verification and what's called delegated computing or blind computing, which is, I claim to have a quantum computer, you do not. You want me to do a difficult computation for you, but you don't trust me. Right? How can we still work this out? And there's protocols for doing that kind of thing. So that's another thing that quantum informatics is very good at. Next question is, when should we care about this sort of quantum computation? And the answer is right now. Quantum computation has been going on in the public eye at least since the 1980s at the very least. In 2019, this is the paper, the cover of the journal Nature of 2019 edition. Google did an experiment. They built a quantum computer that solved a certain problem faster than classical computers could possibly do in 10,000 years. There was some discussion about whether these 10,000 years are really 10,000 or more like 1,000, but the point is quantum computers are really, really, the day has arrived when they are quicker at this problem than any other computer. Now, that problem that they solved is fairly artificial, and we're still debating about sort of solving general problems when the quantum supremacy day, as it's sometimes called, will be there, but it's not too far off. So, but there are some challenges to scaling this up. This was sort of a proof of concept problem. If we really want sort of full-scale quantum computing that's societally useful, we're going to need to scale this up. And I'm going to end with giving you, I think, 4 challenges to scaling. The first one is noise. So these quantum bits that we currently have, they're built in certain different types of hardware. These types of hardware are still very noisy, so they sometimes don't do what we want, and sometimes they're influenced by other factors that we don't care about. So when you ask a quantum bit, what is your value? It gives you the wrong answer some of the time. And one way we can fix this is with what's called error correction. There's methods to suppress these errors and work with these errors. That means you will need more qubits to do less amount of work, but these qubits are now better behaved and they're actually useful in that sense. So there's something called the fault tolerance threshold, which is in this graph, the upper left green zone, so to speak. Once we hit that area, then we can do full-on universal quantum computing for all problems we might like at the scale we might like. We're currently sort of in the bottom left, and we're slowly making our way up to the top left. But actually, this preprint that you see on the right is very, very recent of this last month, I guess, where Google now claims to have made a fault-tolerant quantum computer that beats this threshold. So it's actually very exciting times. Still, noise is one of the major challenges to scaling. Second challenge is sort of related to the first, is we have these quantum computers. You can't quite go out to the shop and buy them, but if you have enough money and you go to various hardware providers, you can just buy quantum compute provision. They've been building more and more qubits of better and better quality. This slide has IBM's roadmap, which goes in 2019 from 27 qubits to last year about 1,000 qubits. It's a bit like Moore's curve, if you know that. That says that classical computer power doubles every year. There's a curve like that of which you see a tiny bit here for quantum bits, and we're sort of bang on that curve. And in some sense, scaling up is really only a question of engineering. Of course, these are formidable challenges, don't get me wrong, but there's nothing in the way of scaling up in principle. Third challenge to scaling, and this is what we do at the University of Edinburgh for a lot, is software for these quantum computers. So for classical computers, there's a whole stack of abstraction that you see here that goes all the way up from the application of, I want to, solve this certain problem, all the way down to how does that get more and more concrete, more and more translated down to how are these transistors in your computer or your phone or something actually turned on and off. So many quantum information research happens at the very top level. Many of the quantum hardware provision engineering happens at the very bottom level, and there needs to be this stuff in between. And that's a challenge. We have some ways of dealing with that, but to scale stuff up, the software needs to improve, basically. And the final challenge to scale I'm going to mention, and then I'll hand over to Oliver, who tell you how we're going to solve all these challenges, is people. The other thing you may have heard in the news, and this is that the quantum technologies landscape and quantum computing in particular is really exploding. Here I've got 3 slides from a report by McKinsey and Company, a well-known consultancy company that track every year how various sectors in the economy are doing, including the quantum economy. And you'll see that this is growth all over, and there's terrific numbers, like $2 trillion by the next 10 years will be the worth of this market. There's by far not enough people to go around, and everybody's screaming for people. We need to train more people in the art of quantum computing, I guess. And that's the final challenge to scaling I'm going to talk about. Next, I'm going to introduce you to Oliver Brown, who might say his own name and say that he worked for EPCC, and tell you a bit more about what kind of applications quantum computing we are doing and how we're planning to solve these challenges. Oliver?
Yes, thanks, Chris, for that introduction. And I will share my slides. And as Chris mentioned, I do indeed work for EPCC, who many of you may know are based in the Bay Center on floor 2, and sitting right now. So to begin with, I'm going to introduce the Quantum Software Lab, to which we all belong. So the Quantum Software Lab was founded by Ellen Kashefi, I want to say 2 years ago now, hopefully that's correct, as part of her becoming Chief Scientific Officer of the National Quantum Computing Center. And the Quantum Software Lab's mission, well, first, let me take things back a little bit. Chris has already introduced quantum informatics and quantum computing. I want us to think for a short second about what is a quantum computer. The word computer dates in English back to at least the 17th century and really means a person, and it was an occupation, and a computer was a person who would solve problems using mathematics, or for the mathematicians in the audience, using numerics. So that being the case, a quantum computer is merely a quantum enhanced device for doing exactly that, for solving problems using mathematics. These days, we're lucky enough to have electronic computers primarily. We don't need people to do this anymore. We have electronic machines that do it much faster. But a computer always has effectively two parts to it, one of which is the hardware, the device itself that does things. So in an electronic computer's case, that's the transistors and various logic circuits. For a quantum computer, the hardware is some two-level quantum systems that we call qubits and means to control them. And then there is the software, which is all of the instructions that are provided to that hardware that tells it what to do, what the problem is it's trying to solve, and how to solve that problem. And that is what the Quantum Software Lab is focused on. Everything from theoretical algorithms that would run on a quantum computer all the way down to the software that would control the quantum computer itself is of interest to us, but nothing that sits below that. We're not interested in hardware other than using it. And crucially, what the Quantum Software Lab wants to do is to try and have a quantum computer do something useful. And I'm going to expand on that a little bit more shortly. What do I mean by useful? But that's the core point, is that a quantum computer must be a device that solves problems. And what the QSL aims to do is to make sure that we can actually solve problems with these devices rather than just creating lots of new ones. Now, as Chris mentioned, one of the big challenges for quantum computing and quantum mathematics in general is the workforce. Simply not enough people right now to help us solve all these problems that we have with quantum computing. We are lucky enough, however, that there was a successful bid for the quantum informatics CDT. So the CDT, Center for Doctoral Training, for anyone who doesn't know, will start next year officially, although we have a small cohort of students actually beginning this year as well, through a separate program, but going through the CDT process and courses. And it covers a wide range of areas from high-performance computing, which, as you might imagine, is my area, working at APCC, all the way through to complexity theory and algorithms. As I said, we like to cover that entire range from hardware up all the way to algorithms. And we have many sites in the CDT across the UK and many academics already involved. But we're always happy to talk to people who are interested in quantum computing, and in particular, people who are looking at ways of applying quantum computing to problems they may have. And we have hopefully a large cohort of students who will also be interested in these kind of things coming soon. But yeah, that will be a big part of trying to help solve all the problems of quantum computing. To get it to be useful, we'll simply be creating this talent pipeline of people that are interested in solving those sorts of problems and advancing computing. So, applications of quantum computing. I'm going to be very brief on this because we have two much more detailed talks coming up from Ross and Mario on specific applications. But to expand a little bit more on what it means for a quantum computer to be useful, let's first of all talk a bit more about Shor's algorithm, which Chris already introduced for integer factorization. So interestingly, Shor's algorithm is mostly classical number theory. It has a very small quantum kernel, which finds the period of a function, which is represented by this circuit on the slide here. But it is only a small part of it. So one key thing to remember is that quantum computing is not some replacement for all of the computing that we know already, but hopefully should fit in with it, integrate and help us accelerate things we're already doing. Now, the advantage of Shor's algorithm is it has an exponential speed up, although if you have good eyesight, you may spot the word algorithmic in there. One thing that's important is that, I mean, basically my entire career is based on the fact that the difference between an algorithmic speed up and an actual speed up, where you get something to run faster, is really large. So it is challenging to be able to run a Shor's algorithm in such a way that you would really do things faster. But it is an interesting challenge and an important one for the future of quantum computing. The downsides of Shor's algorithm are, first of all, that it is not a particularly interesting application, in my opinion. As Chris mentioned, it is important that this is hard to do for the sake of years' worth of RSA encryption. But I can't think of that many applications of integer factoring that actually benefit people in any way. There are some, but mostly those are at a scale where it's much easier to solve as well. So it's worth noting that just because there is this exponential algorithmic speed up for integer factorization, and integer factorization is in general hard as a problem and a complexity level. Actually, we do integer factorization all of the time, every day. If, for example, you want to distribute an array of elements across an arbitrary number of processes in, say, a large HPC system, you do an integer factorization to determine how many elements should go on each processor, for example, or how many processors in each direction of a grid, things like that. So we can solve this problem, and we do regularly. It's just that it doesn't scale particularly well. So when we get to very large numbers that we need to factorize, it becomes impossible to do in a reasonable time. But when we talk about useful applications, it's important to remember that ultimately we should be trying to think of applications that benefit people somehow. Nevertheless, it is important that we know how hard it really is to factor integers, precisely because of the security implications if it is easier. As a bit of relief from the worries of security being broken, it's worth noting as well that Shor's algorithm is not really practical at any reasonable scale on near-term quantum devices either. It requires a lot of gates to implement, precisely because of the scale at which is required to operate. But there's one application of quantum computing. Another perhaps more interesting and more useful one, though, is, as Chris already mentioned, optimization. And in particular, combinatorial optimization works particularly well on quantum computers. This is a very general type of problem in which we have a set of binary choices to make and want to find the overall best one. And what's interesting about this particular application in my mind is that we can solve this using a different type of quantum computer called an annealer, which effectively is cooled down, and by the time it gets to very close to 0 Kelvin rather, it should be in a state that represents the answer to your problem. And this is fantastic because these kind of combinatorial optimization problems come up everywhere. They're widely used in operation research, for example, route planning or resource management. And the best thing about it all is that it just works. This actually works very nicely and does what it's supposed to do. And it works now and scales up very nicely. The downside is that so do all the classical methods. So there are many, many good ways of solving these problems classically too. So this is actually quite a hard target for quantum to beat, not just because the hardware is new, but of course all the software that goes around it is new as well. And whereas the software that solves this on classical computers is very mature because it's an important area for many, many industries. So we have a lot more work to do in applications like this, where although we can demonstrate that the quantum computer solves the problem, it's much harder to demonstrate that it solves it better than the classical computer, simply because the classical computers have decades worth of research already in them and how to do it as efficiently as possible. The other downside of this approach is that you need to map your classical problem into a quantum one in order to solve it this way in the first place, although we do have some good ways of doing that. So there's a very brief view of a couple of applications of quantum computing, one of which I would say is more useful than the other. And with that, I will pass you on to Ross, who's going to give us a much more detailed talk on the area of quantum machine learning. Ross, take it away.
Hey everybody, hang on if I share my slides here. Hopefully we can all see something that says quantum solutions for fraud detection now, and can't see any of my Zoom controls. So yes, hi everybody, so I'm Ross Grass. I'm the technical program manager for the Quantum Software Lab. And I'm going to very briefly tell you about some work that we've been doing in quantum computing for finance, working with these partners here, HSBC, Rigetti, and the National Quantum Computing Center. And I think hopefully what I'll show in the next few slides is that just because it has the word quantum in front of it shouldn't make any of these projects any more scary than if we're using any other emerging technology at the moment. The way that we go about thinking of where we're going to put quantum into existing workflows is precisely the same as if we said machine learning, we said AI, or anything else for that matter. So I'll start off with some very simple questions about why we were interested in this particular application. So what were we interested in? We're interested in fraud, which is just knowingly deceiving another party for some financial gain. Why is it important? UK finance lost 1.2 billion in 2022 due to fraud. That number actually went to 2.3 billion in 2023. So this is something that, as an economy, we should really care about, and we might be thinking of trying to use the best technology available today to try and solve this problem. And when is it important? As with quantum computing, it's important now. There's a number of things happening in the world which mean that the number of scams and attacks are increasing, not least cost of living crisis and AI. People are using ChatGPT and generative modeling to not only write their essays for them, but also to design new and interesting attacks for fraud. And how could we think about tackling fraud? Normally it's kind of split into prevention, detection, and mitigation. In this particular project, we're just going to concentrate on the detection aspect. And who is involved in this? Well, governments, banks, and regulators are the people who are generally on the front line trying to catch fraudulent instances, but it kind of affects everybody in the entire economy, whether it's your money that's being stolen or you're being impacted by the way that that stolen money is being spent. And then just very quickly, this is the fantastic team of people we have working on this project. But notice as well, so far I've said nothing of that is quantum specific. This is all an application that's of interest, and we're just using a new method for trying to solve this problem. And at the Quantum Software Lab, we have this Quantum Advantage Pathfinder program, which we like to use when we're thinking about these application specific problems. So we were talking with HSBC, where we picked an industry pain point. We developed a use case with them. We then translated their industry problem into an academic problem so that we could give that to our researchers to design, implement, and benchmark new solutions until we end up with a product. And then because we're an academic group, products look like open source software, academic papers, white papers, technical reports that will be interesting for industry. So we spoke with HSBC. They wanted to work on the number of fraudulent transactions they saw going through their system. So we developed the fraud detection use case and found that it's just a classification problem at the end of the day. If you're given a new transaction, you want to classify it as either fraudulent or non-fraudulent. So we've got a number of different methods for solving this that we're designing in the consortium, and we'll very quickly go through two of them, one based on support vector machines and another based on gradient boosted decision trees. Again, both of these coming from classical machine learning, and all we're going to look at is quantizing just part of these existing methods. So the support vector machine solution already kind of existed within HSBC when we started this project. And from classical machine learning, the intuition is that if we have our transaction data in some space where it's very difficult to find the fraudulent ones based against the non-fraudulent cases, all we want to do is map the data into a new space where defining this decision boundary is much easier. And then the central mathematical component of this is this kernel, where it's just defining distances between data points in this higher dimensional space. So all of this is completely classical machine learning. It has nothing to do with quantum yet. And then our quantization of this classical machine learning comes through using a quantum feature map. So when we're mapping from here into this far nicer space, we think of using a quantum circuit in order to do that. So everything else in the process stays as it was before. All that's going to happen is the calculation of this kernel is going to be sent to a quantum computer. We'll get back a classical solution, which will then go into the workflow as it was before. So as Oliver said, we're looking at quantum computing complementing classical computing, not replacing it. So the ongoing work that we have here is that we want to create a bit of a comparison framework. We have a number of other methods as well as this one. So we want to be able to pick one or two methods, choose a particular implementation, whether we're going to run it in simulation or we're going to actually run it on quantum devices, pick the tests that we're interested in, whether it be inference time or retraining time or the quality of our classification, and then just give us a comparison. The other bit of work that we're doing is trying to improve this feature map as well. So we have a tool that we've developed within the quantum software lab where we can look at these circuits and try and capture the correlations that we're seeing in the data in our quantum state better than we do classically. So we're using that toolkit to see if it can improve the accuracy of our classification between fraudulent and non-fraudulent data points. The other method that we've been looking at is gradient boosted decision trees. Again, this is a method that is implemented in practice by banks at the moment, well, variations of. So these are really nice models in that they have fast inference and good accuracy, but they can be very slow to retrain. So if I get last quarter's transaction information, trying to incorporate that into my new model can be very slow. Classically, still, there are a few methods that people have come up with in order to improve this retraining, and one of them is light GBM, which has these two pre-processing steps that they do to try and improve the training speed. So what we did was we focused in on this effective feature bundling subroutine, because mathematically all this maps to is a graph coloring, which there have been quantum algorithms recommended that will be able to do it better than their classical counterpart. So we're taking this full gradient boosted decision tree framework, picking out a subroutine that we believe can be done better on a quantum device, and just asking, if we do this small replacement, is that going to give us an improvement in our classification? So when we go back to our quantum advantage pathfinder, this is roughly where these two methods are at, where we've got our light GBM currently getting implemented, and we're currently benchmarking the support vector machine against the classical state of the art, and we're hoping to have a few papers come out soon where we're doing this comparison. But some kind of key take-home messages that I wanted to highlight were that we very deliberately picked fraud detection because we're still in this era where these improvements that we could see from using quantum solutions over classical solutions, they were likely to just be fractional improvements. So we want to pick use cases where fractional improvements still make a very big difference. So if we saw 1.2 billion getting lost due to fraud, if we can improve that by 0.1%, that's still a lot of money being saved. So we're very deliberately targeting these kinds of applications to have a look at. And also wanted to highlight that this thinking about this problem and trying to come up with a quantum solution means that we're actually getting very competitive new classical solutions as well. So doing classical simulations of quantum circuits and looking at quantum-inspired solutions means that we are still seeing improvements in fraud detection rates, and that's before we've even put a quantum computer into the workflow. So I think that's an interesting point that is sometimes lost, is you don't always need the final solution to be fully quantum. Just by thinking of it in this new way, we may get some very interesting new ways of solving these old problems. So that's it from me. And I think next I will pass it on to Mario, who's going to talk about genomics research that we've been doing.
Hi, everyone. So hopefully you're seeing also a title which says Quantum Generative Modeling and Potential for Enhancement in Genomics. Okay, perfect. So what we try to do here, the main message is that we try to enhance the understanding of the system correlation and their higher order interactions. And yeah, so this is what we want to do. We want to retrieve interactions in complex systems. These are everywhere, and this is what gives us the phenomena, the resulting phenomena. So, for example, interactions between atmospheric conditions, resulting weather patterns and climate phenomena. Also, mathematically, we can say that the interactions between particles will give us the physical state and phase transitions. Between financial agents, we will have the market behaviors and economic outcomes. And the interaction between neurons will give us our neurological functions and disorders. But more specifically, for this application case, we are going to treat these two patterns of interactions, interactions between genes and diseases and cancer, and interactions between weighted connections that result in the patterns and learning phenomena. So this is basically what ML mainly does, and we will try to retrieve these ones. So how to do this? There are two ways, and I will quote Richard Feynman. And the first way is the forward problem, where we take the parameters and we obtain the data. So what I cannot create, I cannot understand. So we try to get the interactions mathematically and then produce the data, or we can go the other way by taking the data and actually obtaining the parameters, not mathematically. So this here I cite myself. What I cannot infer, I cannot understand. And now the case which we were motivated from came from researchers here in Edinburgh. And what they did was basically develop this stator method, which their aim was to determine the type of cell under the state. So basically, we take cells from the mouse brains, and we obtain the interactions. So these sub1s are the interactions. Then we do a hierarchical clustering, and the pipeline ends by obtaining the signatures. So this worked, but they were only able to do it up to 1,000 highly variable genes with up to also like 40,000 cells. So our aim would be to try and improve the capabilities of this pipeline by just targeting this small section here, while we only want to retrieve better, better quality interactions. However, at least out from the box, just because it doesn't work well in classical doesn't mean it's going to work perfectly in quantum. So we scaled down the problem to a case where it was not so complex and that we understand very well. So there has been plenty of PhD theses actually describing this model here, which is the one-dimensional transverse field Ising model, which in some way tries to reproduce what happens with the gene states, because here we have a chain of spins, up and down, and what we want to retrieve is how they interact. For some of you, the people who know, this could represent magnetization. So what we do basically is we retrieve the data, as they said, and we obtain our training distribution. So this shows the probability the B string 0 appeared, and then we do that for all the B strings. 1 represents spin up, and down represents, one represents up, 0 represents down. And now we try to match it up with a distribution that we obtain with a quantum computer. This quantum computer or quantum algorithm will be based on a variation algorithm. This means that what we are going to do is vary some parameters that are encoded within our gates of our quantum computer to try and obtain sample data. So this sample data will be, again, ones and zeros, meaning that we can actually compare with a loss function the probability obtained from our spin chain and the probability obtained from our quantum, what we call circuit board machine, what is just the variation algorithm I was talking about. So that's the objective. And for the pleasure of your eyes, like here's like what's actually training in a quantum computer looks like. So as I said, we are trying to match up the two probability distributions. So here we see in pink or red the one from our quantum computer, and notice that this is at the end of the training. So once we have obtained the actual parameters that we know minimize our function, and they match up with the blue one, which is like our ground truth or our Ising model. Now here on the right, we have like a exact solution. And what do I mean by exact solution? We mean we have simulated, we have left a lot of time for example, my laptop or like a cluster to run. And this is an exact solution because the quantum computer actually has noise. And this is a barrier that we still need to overcome, and a lot of people are working on. So what happens when we just use the quantum computer without trying to what we call mitigate this noise? So we have like this yellow line here. The loss function doesn't really go down. So here I'm plotting the loss with respect to the iterations or epochs. And it doesn't really go down that much because noise is influencing quite a bit the training. However, when we apply techniques from quantum mitigation, we're able to obtain the dark brown curve and be close to the exact solver. However, this is not enough. Like it's difficult to actually say if we've done good or not. So what we do is try to get some metrics, which we call actually the interactions that we are after. So here we see that we have one point interactions, and we match them. Again, the blue is the Ising, what we expect from the Ising model, and what we hope to reconstruct with the quantum circuit board machine in pink. For the 2-point interactions, they are a bit more complex, so therefore there are more errors. And then for the 3-point interactions, we are also able to obtain it up to some fidelity. So this is how we are assessing it and then benchmarking it. We still need to explore how to improve these quantum approaches, because in this quantum circuit, there's a lot of things that we can do. As I said, out of the box, we don't know if it's really gonna contribute, how the interactions are given in this quantum circuit make the training go worse or better. So this is a very important point that we actually treat with theoretical knowledge. And what we're trying to do right now, which is I'm actually running right now, is an implementation in small biological data sets. And with the hope of actually scaling up to quantum solutions. So the take-home message here, quantum is quite a new technology, and they still have a lot of study to undergo. So, but the main thing that we have been proving here is that we're able to infer what I was talking about at the beginning, the underlying interaction from data. Now, as I said, the quantum algorithms are still, like, at least for the variational case, which is the one that I explained, are not at their best performance. So we still need like some classical assistance, and maybe with this even to design like classical quantum-inspired solutions. And we're actually going to publish this soon. So if you want to stay tuned, and in this publication wouldn't be possible with all the team, also from the National Computing Center and the Quantum Software Lab, and also like with teams up with the mathematicians in the biology groups in the University of Edinburgh. Yes, I think that's it. Thank you.
Thank you, Mario. I hope those 4 presentations have given you a bit of an overview of what quantum informatics is all about and how it might be useful to you. We have some time in the agenda for Q&A. So if you have any burning questions, we are very happy to try and answer them. You can either just unmute yourself and shout, or type in the chat as you prefer, and I'll try to make sure everything goes appropriately. So please ask away. or if there is a deafening silence, I will take that as a sign that everything is crystal clear and we've done our job well and I can sleep well tonight.
Sorry, I have a question.
Please shoot.
Don't know if you can hear me. Yeah. I mean, you have mentioned that quantum computing could be used on real case scenario. So do you have any timeline or a roadmap when some of the innovation, especially, I mean, in areas like the logistic sector, could be used? I know you're doing some testing with banking, but is there like a expected timelines? Now you have the CDT and you know, more people taking interest in the subject, where you know, we can have some real case, at least TRL6, you know, between 5 to 7, that we can take it to market?
That is a very hard question. Thank you for asking it, because it's very difficult to answer. It's very hard to predict the future. As I was saying, there's this sort of Moore's curve of how the hardware is going to develop. We can sort of extrapolate some timelines based on that. At the same time, there's, of course, progress in how quantum computations are optimized and how advances in algorithms that will bring down the need for however many qubits are needed for that application. But in principle, this is a whole research area called resource estimation that's trying to pin down, you know, when, if you're going to solve a problem this and this big, when exactly are the means going to be available to do that? And I'm not today going to put my hand in the fire, say that the answer is, let's say 3 years, because I simply don't know. I'm sorry, it's a bit of a cop-out, but that's what it is.
I don't mind being a bit more controversial, so I always like to say that I reckon I'll be retired before we see anything really useful happening with a quantum computer. So about 30 years, depending on when the retirement age is by the time that I get there. I think we'll be a long way towards that, but I don't expect to see quantum as an accelerator going, you know, full bore in a HPC setting before that time, really. Because I think we'll be a long way towards it. I think there will also be a couple of like niche applications where we actually do see it being used in the wild long before then, but it won't be widespread.
So where do you think is the lagging? Is it, or probably I will rephrase it in another way. Where do you see the most advancement happening at the moment, in the software side or the hardware?
Hardware.
You know,
that's an easy question. Hardware is way ahead of the software. Yeah. In
Mm-hmm.
part because it's hard to write software for hardware that doesn't exist, or is not as performant as you need it to be to demonstrate things. But also just because it takes time. So I always give GPUs as an example. The first paper that said you could do linear algebra on a GPU came out in 2002, at the same time that DirectX, the drivers for graphics cards, added floating point support. Floating point numbers are how we do most scientific and engineering applications, right? It's anything with a decimal point in. And it took about 20 years for GPUs to be integrated into the HPC ecosystem to become ubiquitous in the way that they are now. And that was all just software work. There was almost, I mean, GPU hardware has advanced, but it's mainly just been sucking in more power to do things faster. But it hasn't fundamentally changed in that time. It's all been software.
Now we have NPUs as well. So that's another advance. So
Indeed.
Quantum is trying to catch up as well. Mm-hmm.
Well, yes, exactly. That's the other point, is that classical computing has not stood still while quantum advances. So it takes a lot to overcome. And in particular, so the nearer term applications, I think, are things like the operational research areas where, you know, those combinatorial optimization problems map really nicely to quantum computing hardware. But the problem is there's so many really good ways to solve those problems classically. It's quite hard to find the areas where you actually do see an advantage from the quantum side at the moment. But that could change overnight with the way that hardware advances, as long as we can program it well enough that we can rapidly try out the new hardware when it appears.
I can maybe add to that you should think about current quantum hardware as classical computers were in the 1960s, roughly. So we didn't really know how to operate them, and everything was a bit ad hoc. Because this programming a quantum computer is really a different experience from programming a classical computer, and you can't just take a computer science graduate and expect them to do it. They need to know a bit about physics and quantum informatics generally.
Yeah, that's what I was thinking. Like maybe it's a totally change of mindset, you know, rather than replicate classical computing and classical software pattern, it will be like something completely different, like a new theory to accelerate the software development within quantum. But I don't want to capitalize all the questions because I have seen on the chat quite a few others as well, but thanks very much.
Thank you. Yes, I saw there were some on the chat. Katie was asking, what do we see as the biggest opportunity? So we talked about some sectors and applications, specifically finance and genomics. That's in some sense a coincidence because, as we were saying, optimization, for example, is a hugely broad problem that quantum computers are typically good at, and you know, any sector will be interested in optimization problems. But it's also not a coincidence because these are typically sectors that have deep pockets and that can afford to put a small team on something just to check out whether it's worth it. So I'm not sure if that's a very useful answer. And maybe some of Mario or Oliver or Ross would like to add something to that.
I would say also material science, as it seems natural for a quantum computer to actually describe the physics behind. And they actually have good money to actually invest in smaller groups. So I would say that one looks very promising, yes.
I was going to add material science, anything to do with kind of chemistry, anything that kind of, I don't know, problems that you're asking are kind of naturally about things that will see quantum effects are good places to look. And then, yeah, ones like anything logistics, finance, as Chris says, they have more money to try these things out. So they are those kinds of companies are generally a little bit further ahead in their thinking because they've been able to hire one or two people at a company to make the case for whether they should care about it or not. Whereas in other sectors, that's maybe a bit harder to do. Yeah. Oliver looked like he was going to add something to that, but no.
No, I think that's exactly it. Quantum problems are a promising place to start, and then anything that you need a bit string at the end of. There are technical reasons why that specifically is useful that we probably don't have time for right now, but yeah.
Thanks. Thank you.
All right, and then Lucy is asking, what are current constraints on access to quantum computers, and are you able to do as much processing as you would like? That again depends a bit on your means. You can go to commercial hardware providers like IBM or Google or Rigetti. There's several ones. They offer different platforms. Most of them are accessible through the cloud. Some of them will build a machine and come and install it in your house. So depending on the amount of money you're willing to spend, you can have loads of access. For public sector things, the National Quantum Computing Center is currently in the process of installing 7 different what they call test beds. These are supposed to be available to at least scientific purposes and maybe commercial purposes if you go through an application process, but that should be lightweight. In addition to that, many providers have, like IBM, for example, or Xanadu have education tier access just for people wanting to learn about what it's like and how you can operate APIs for these kinds of machines. Most of them are free, but they will have they go down in the queue of priority of when your job will be executed, or they can maybe have only access to some of the older models that have more noise or fewer qubits or something like that. I hope that answers your question.
Just to add on to that, maybe the other option, if you have access to large classical computers, is you can always simulate things. And there's a number of good simulation packages. And actually, a lot of what the Quantum Software Lab does is done in simulation. Because if you are trying to develop an algorithm or verify that an approach works, sometimes actually a simulation is better than the hardware for that kind of work. On the flip side, if you want to do answer questions like how will I interface with a quantum computer from my large Fortran code, for that you really do actually need some kind of hardware access, and particularly of a kind that the commercial vendors are not necessarily keen to offer us. Put it like that. So there are challenges around hardware access at the moment because quantum computers exist, but they are hard to find.
Right, there's a question from Cameron who asked, if hardware advances take longer and longer, do you think there's a risk of attention of society will shift elsewhere? That's more of a sociological question, which I'm not sure, we are qualified to answer, but that's certainly a risk. Having said that, though, there is some sort of ground truth that we're not going to be able to escape from, in the sense that if, let's say you're the government, and you have things you want to keep secret, then if another state actor is working on quantum computing while you are not, they can now, from today on, record all your communications, and then whenever they have enough capability, decrypt them then. This is a store now, decrypt later kind of attack. And that's something you just cannot get away from. To the sociological question, I'm not really sure what to say. What do you think, guys?
I think it, definitely is a risk. I think the thing that's on quantum side, as it were, is the kind of end of Moore's law scaling. So we're already starting to rely on more niche accelerators, and they have, in many ways, the same problems that quantum has, in that they're hard to program, hard to make use of, and hard to exploit efficiently. So quantum is not much worse off than things like TPUs or wafer scale chips and things like that, in that sense.
Just looking at the chat, thinking of consequences for funding, essentially, which I guess is an interesting question right now in the UK. But yeah, I think if the hardware's maybe not progressing as fast as people are expecting it to, then maybe there is this we should be a bit scared that funding will get siphoned off and go elsewhere. Yes, it'll be interesting to see if we already start to see that a little bit, at least with things like, well, AI is the big one at the moment. When I first started doing quantum computing, quantum seemed the most interesting thing. ChatGPT came along, and actually the focus kind of shifted onto generative AI, and people started buying much more GPUs and seeing what they could do. If budget cuts come, maybe they think generative AI and AI in general has more near-term use, so therefore some quantum funding gets cut. That's not inconceivable that could happen. But I can't see, because of the kind of national security aspect of it and stuff, I think there'll always be a level of funding there that will stick around. And also, it is looking promising that quantum computing will be useful for logistics and things. So I can't see it completely vanishing. So hopefully that kind of answers the funding aspect of it.
I can add to that, Ross. It's not just an arms race between countries, but there's also an arms race in an economic sense, because there is a fledgling what's called quantum economy. The UK is doing quite well, and there's a lot of jobs to be created and money to be made there. So I think any smart government would keep some funding on quantum development. The current one is doing that. They have what they call the quantum missions. There are 5, and they're spending, I forget the numbers, but large amounts of money on there. Whether that will continue going, time will tell, I guess. I'm aware that we're running out of time. There's a last question that we can maybe take from Robin, who's asking, in order to determine what suitable applications there might be, it's probably best to actually try things out. That makes total sense. There's a slight paradox at the moment in that the facilities don't exist. I'm sure EPCC will have something when Oliver retires. But how do non-quantum folk try things out at the moment? Are there simulations on classical systems that are easy to use? Maybe I can give a first answer. I'm sure Oliver has much more to say. There's many open source packages that you can just go and download, execute on your laptop, but of course your laptop will be limited in how many qubits it can actually simulate. If you want to simulate larger things, you're going to need to have a larger classical system, but the means to do so are perfectly open source and available to everybody. And also many of the, for example, IBM educational Q experience, as they call it, you can just sign up, make an account, you don't need anything. They have simulators built into their web interface to their programming system. Oliver, I'm sure you want to add something to that.
Sure, yeah, thanks, Chris. Yeah, but so simulations on classical systems are no harder to use than actual quantum computers, and in many cases easier, for various reasons. In part, it's that if you do an exact simulation, you actually get more information out of that than you can out of a quantum computer for reasons related to what's called the measurement problem in quantum theory. But suffice it to say that yes, it's certainly possible to do a lot with just simulation, and indeed we do. And in particular, part of EPCC's core activity in quantum computing is precisely on making sure that we have the right classical tools for simulating quantum computers at various scales. So, of course, people can do lots of things on their laptop, and for a lot of work, that's perfectly fine. But for anyone who needs to go bigger, then we've been looking at distributed state vector simulators, called a particular one called Quest, which scales up to basically the entire size of Archer 2, the UK's national supercomputer. And we're also, at the moment, investing a lot of effort into something called tensor network simulation as well, and seeing how we can do that. But yeah, plenty of ways to go about it with no actual quantum computer involved. And as I say, for applications work in particular, the actual hardware can sometimes make things worse rather than better.
Maybe a final thing I can say is we haven't touched on it so much, but there's also a lot of quantum-inspired classical things you can do. That means that if you're thinking in a sort of quantum way about classical situations and structures and algorithms, that often inspires new things that we haven't found before. So in that sense too, there's a lot of things you can do yourself without having any quantum computers. But I realize it's past 1 by now, and I thank you very much for all giving up your lunch breaks and being willing to learn a bit about quantum computing, and hope it has been useful to you. If you have any feedback afterwards, we're very open to just answer email. You can find us on the web. I sound a bit like a YouTuber now, so I'll just stop there. Thank you very much. Have a great day.